Okay, so we're going to be talking about periodic table, bonding types, and names. So that's what we're going to be dealing with right now. I'm going to go ahead and share my screen again, and let's get rid of this so that we can look at some things. Get back to my periodic table. So here's my periodic table. Now, the one that you're seeing right here doesn't have any symbols or molecular weights or any of that on there. We do have a link to where it comes from, and we're going to be talking about some of the things that exist in this. Now, I'm not going to need my paper so much with this one, so I'm going to make this bigger so that we can see it in more detail. And I'm actually going to do a slideshow on this just so that we can see everything. So again, these are links if you need them to be able to get to these particular topics in your textbook. So looking at my periodic table, my metals. Metals exist everywhere to the left of this stair step. So this stair step is where the metalloids exist. So they have properties of both metals and nonmetals. So those are the metalloids. Everything to this side and everything down here, those are all my metals. So most of the table are metals. The nonmetals is this stuff over here. So this corner and this down here. Those are my nonmetals, okay? So my metallic character increases as I go down and to the right or to the left, and my non-metallic character gets higher as I go up and to the right. All right. So that's what we're looking at there. We can talk about effective nuclear charge. Now, what happens if I'm talking about a particular row? And let's talk about the second row right now. So this row that exists right here. And oxygen is in here, nitrogen is in here, fluorine is in here. Those are the ones that we're talking about right now. So as I come into this, I'm in that second row. So I've got a 1s2, 1s1, 1s2, 2 electrons that exist there. And let me remind you that these are my s groups, 1 and 2. Those are my s groups. 13, 14, 15, 16, 17, and 18, those are p electrons that we're filling in. 3 through 12, those are d electrons. And then these ones down here, the lanthanides and the actinides, those are f's. Okay. As we go across, we have this one, which is hydrogen. It has 1 electron and 1 proton. We then add an additional electron and proton to become helium. So my electron configuration here is 1s1, and here for helium is 1s2. As I come down to lithium, which is number 3, that's 1s1, actually 1s2, and then 2s1. So that's how we get there. So, and then if we were going to go the next one over, I can't remember which one that is, that's 2s2. Okay, so we have those things that we talk about there. Now, as we come across this row, we add additional protons to that nucleus. So we have our nucleus that has 2 protons in it when we get to lithium, and then we add an additional proton to the center. So now I've got 3 of them, and they're not protons, they're positive charges, sorry, in the center. So I've got 3 of them. So there are 3 of them. There's 2 in the very, very middle and 1 outside of that. And then I've got 3 electrons that are going around. 2 in the tighter in, and then 1 further out. But those 3 electrons don't really see each other, but they do see all of that charge in the middle. So as I continue to add stuff in that same shell on the outside and have this bigger charge in the inside, things pull in. Okay, so as I go across this table from the left side to the right side, things get smaller. And that's because of the higher nuclear charge. It looks to be in a more effective nuclear charge. Okay, so our effective nuclear charge is that we get smaller as we go across to the right. Now, the other thing that we can deal with is that we get smaller as we go up. So they're bigger as we go down and smaller as we go up, obviously, because we have less stuff away from the nucleus when we do that. Now, our atomic radius is going to mimic that. So where we have a higher nuclear charge, we're going to pull in more. So that means that our higher nuclear charges over here, on the right-hand side, are going to have a smaller atomic radius. Now, an ionization energy is how much energy it takes to be able to pull an electron off of a particular element. So again, if we're talking about lithium, we want to know how much energy is it going to take to remove that outermost electron, the 2s1, from that thing. Now, for reasons that we'll talk about, everything in the universe wants to be a noble gas. Those noble gases have what we call a stable octet. So they have 2 s electrons and 6 p electrons in their outermost shell. Remember that the D's and the F's are interior to that. So their outermost shell is full with 2 s electrons and 6 p electrons. Everything else wants to get to that. Okay, so our group 1 metals, the alkali metals, want to lose 1 electron to become like the noble gas before them. So lithium wants to become like helium that has a 2s2. Now it's not an octet for that one, that's a duet, and that's because we don't have any p's that we're filling. It's all s that we're talking about there. Okay, but that's how it's going to get back to that. And our alkaline earth metals also want to lose 2 s electrons to become like the nearest noble gas. When we move to the other side, however, and it depends on exactly which one we're talking about. These metalloids can do both. They can gain electrons or lose electrons. But once we get over in here, they're only going to be able to gain electrons to get to be like the nearest noble gas. So when we talk about fluorine, which is right here in group 17, he's a halogen. He's going to pick up 1 electron to be like the nearest noble gas. Okay. When we talk about oxygen, he's going to pick up 2. And nitrogen, who's in 15, he's going to pick up 1, 2, 3. Okay, so that's how that works. Like I said, we do have some things that go back and forth in terms of what we do. We only really predict charges for the alkali metals, which are these guys right here in group 1, the alkaline earth metals, which are these guys in group 2, the halogens, which is group 17, and the chalcogens, which is group 16. The only other thing that we talk about are the noble gases, and you need to know which column that is. So those are the 5 columns that you need to know the names for. So that tells me about electron affinity. So electron affinity ionization energy is a measure of how much it wants that outermost electron. So the things on this side want to give it up, the things on this side want to take it in, and so it's going to take more energy to pull one off when it wants more. Okay? Electron affinity, on the other hand, is how easy is it for it to pull an electron in. So my electron affinity is going to be higher when I want more electrons and lower when I don't want them. Okay. And my electronegativity is the same trend, but it's different measurement. So electron affinity is how much it takes to take a free floating electron and add it to an element. Electronegativity is how much pull there is for the electrons in a bond between 2 atoms. Okay, we want to see, do they get pulled in equal directions, or like on an oxygen and a hydrogen, the oxygen wants that electron way more than the hydrogen does. And so the electronegativity on the oxygen is way higher. Okay, so those electrons in that bond spend more time with the more electronegative atom. So there we're talking about electrons in the bonds. Electron affinities are for electrons that are not in bonds. So I said there were a couple of groups that you need to know the names for. That's the alkali metals, the alkaline earth metals, the chalcogens, halogens, and noble gases. Okay? You need to be able to write an electron configuration. Now, am I specifically going to ask you about an electron configuration? No, not necessarily. But you do need to know what they mean. So if I say, this thing has a 1s2, 2s2, 2p6, blah, 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 you know how many electrons I'm talking about. And you know that the ones at the outside are the ones that are the valence electrons, okay? So anything in that second row, we're only talking about the electrons that are in that second group. So we're not talking about the 1s2s, we're talking about the 2s2s. And the 2p's that we have. So the 2s and 2p's. Those are the valence electrons. That's whatever in that outermost shell. Okay. We also need to know how to predict ionic charge. So again, we talked about lithium wanting to give up an electron to come back and be like helium. So these guys have 1 electron they want to get rid of. So these tend to be plus 1s. The alkaline earth metals tend to be plus 2s. The halogens tend to be minus 1s. The chalcogens tend to be minus 2s. You're not required to know the rest of them. Those are the ones I want you to be able to predict. Okay. So we've talked about electron affinity, ionization energy, atomic radius, and electronegativity. Okay, so those are those things. And then the metallic character and non-metallic character. So those are all things that you need to be able to predict. And again, I'm not going to ask you directly what are those trends, what do they look like, any of that stuff. What I am going to do is expect that you understand that those things are there and that they affect the chemistry that we're seeing. All right, so you need to understand how that affects what we're seeing in terms of chemistry. Okay, so that's everything I want to talk about with the periodic table. Now, expectations. I want to know, where are the metals? So remember, my metals are everything over on the left side of the table, next compared to that stair step. So everything to the left of the stair step and the stuff down here in the bottom. Where am I? And where? Oh, there we go. So these are the metals. Really bad handwriting. My metalloids are these guys right along the stair step. The nonmetals, and I'm just going to go NM, are the ones over here. Okay. Effective nuclear charge gets bigger as we go across this way. So there's more effective charge on that side and more as we go down. So that's my effective nuclear charge. My atomic radius is going to get smaller as the effective nuclear charge gets bigger. So we're going to be looking at the atomic radius getting bigger as we go this direction. So we get bigger going that way and bigger going that way. Okay. And our atomic radius gets bigger as we go down, even though there's more effective nuclear charge, because we're further away from the nucleus. Okay, there's nothing we can do about that. Our atomic radius within a single group, however, is going to be the opposite trend as the effective nuclear charge. When we talk about ionization energy, we know that it's more effective, so it's a better deal for it to give up electrons over here. So these are going to be our plus ones, these are going to be our plus twos. This is going to be minus 1, minus 2, and minus 3 is typically, although they don't always become ions. So they can, but they don't always. And that's again because the ionization energy for this is very small. And over here it's very large. So it goes up going that way. And it goes up going down. No, it goes up going that way. Sorry. So further away from the nucleus we are, the harder it is to pull them off. Our electron affinity goes up so it wants them more as, no, wait, hold on. I have managed to confuse myself. I apologize. I want to erase this last one that I did. So ionization energy, bigger energy. It requires more energy as we go across this way. So more energy, bigger values as we go across that way, and it requires more energy as we go up. So that's our IA. Our electron affinity, we want to pull them in as we go in the same trend. The thing that's different is that when we're talking about our electron affinity, even though it's the same thing, it becomes more negative, i.e. it's more spontaneous. We'll talk about what we mean by spontaneous and negative and all of that in a few lectures when we talk about thermodynamics. Sorry, I need to get clean. But it is more favorable for us to give those things up as we get over there. So those values are negative. So more favorable, negative. Okay. So they're actually different signs, but it's the same trend. When we talk about electronegativity, we know that that is directly related to how much I want those electrons if I'm in the same bond. So things with higher electronegativity are as we go towards fluorine. So over to the right and up. So higher electronegativity as we go over to the right and up. All right. We've done ionic charge, talked about the number of valence electrons. So when we talk about valence electrons, and we're talking about over here, well, that was fun. I have 1 there. I have 2 there. I have 3 here, 4 here, 5, 6, 7, and 8. Okay? So that's my number of valence electrons. Names. This is alkali metal. So this is the alkali metals, this group right here. These are my alkaline earths. These are my halogens. These are the noble gases. And these are the chalcogens. Okay? So those are the ones that you need to know for that. Now, when we talk about blocks, we're talking about an S block here, a D block here, an F block down here, and a P block here. And what that means is as we add electrons, and we're in those particular groups, we're adding them to that type of orbital. Okay, so that's how that goes. And if you have questions about that, please let me know. Now, I did ask you to do a full and noble gas notation electron configuration for sulfur. So if we want to look at sulfur, I'm going to get out of this, and I want to talk about sulfur. And I want to know sulfur's atomic number is 16. Okay, so he's 16. And that means that if we're looking at a periodic table, I'm trying to see if I have one that actually has numbers on it. I don't know that I do. Yeah, I don't. Bless it. So sulfur's number 16. And I want a periodic table that I can actually look at so that I can show it to you, because I can do this without looking at the table, but that's because I know what I'm doing. Yeah, okay. So we see sulfur. He's right here. Okay, he's in the 3rd row. So I know we're going to have to deal with that. Now, if I'm past the 1st row, that means I have 1 S and 2 electrons in it. Because that 1st row only contains, is principal quantum number 1. There's only an S type in it. It can only contain 2 electrons, and it's completely full, so that's a 1s2. We then go to the 2nd row. The next one we fill is a 2s, because the S type is first. That is completely full, so I have a 2s2. We then go to the 2p orbitals, the ones over here, boron, carbon, nitrogen, that over in there. That is completely full as well, so that's a 2p6. We then go to the 3rd row, where we're talking about Na, and that's a 3s group. That is full. And then we come over, we have aluminum, silicon, phosphorus, and sulfur. Now that is in the 3 group, so that's a 3. It's a p-type orbital, and there are 4 electrons that are in it. So that's the full electron configuration of that thing. Now, the nearest noble gas to sulfur is neon, right? And the noble gas configuration for neon is 1s2, 2s2, 2p6. So those two are equal. So I can write the electron configuration of sulfur as the Ne core, because we don't do any chemistry with the core for the most part, 3s2, 3p4. That's everything in that valence shell, so the outermost shell, and that means that I have 6 electrons in that valence shell, 2 in the s and 4 in the p. Okay, so that's what we're looking at there. All right, let me put that away somewhere just in case I need it again. Awesome. I don't remember. Okay, fine. So that takes us through that. Now, the next thing that we need to be able to talk about in terms of, like, we've talked about periodic trends, we've talked about some things on the periodic table. The next thing we need to be able to talk about is what kind of bonding are we looking at for these particular molecules. The types of bonding is determined by the things that are in it, okay? So if we're looking at our periodic table, and we have metals and nonmetals in that bond, that's a metal to nonmetal bond, then that's going to be an ionic bond. And what that means is that we transfer electrons from the metal to the nonmetal. So we end up with positive charges on our metals, positive charge, and our nonmetals are negative charges. This is a cation, this is an anion, okay? And we match them based on what their charges are. So if we were to talk about Na plus and an O2 minus, in order for us to be able to do that, we'd be talking about an Na2O, because we need 2 positives to match with the 2 negatives. So that's how we balance that. Whatever charge the anion has becomes a subscript on the cation. Okay, so that's how we do that part. So that's our metal to nonmetal. There's our ionic bonds, and that's how we deal with that. And when we talk about nonmetal to nonmetal, those are covalent bonds. And when we do that, we don't have full charges. So we're sharing electrons. Here we transfer electrons. Okay, so we don't have actual charges. We're sharing electrons to get to that octet so that we can have that. Now, I always think about this in terms of where I'm a kid with divorced parents. Where do I spend all of my time? I either am in a situation where I spend all of my time with one parent, or I am shared between those 2 parents in some way, shape, or form. Now, if it's a complete transfer and I only spend time with one parent, that's an ionic bond. So I've been given away from one and given to the other. If I have some arrangement where I spend some time with one of them and the other, then that's a sharing, and that's covalent. Okay, that's important. Because there is a fixed way that our ionic bonds are formed based on the charge, then the nomenclature for that is simple. All right, and that's the next thing we're going to talk about, is the naming of these compounds. I do have some practice here for the types of bonds. I'm going to put the answers for these on D2L rather than going through them right here. I want to get into the nomenclature of the things before we get any further. So I want to make sure that you guys have those answers on D2L, so I'll put that up. When we talk about names, now names are critical. At this point, you're going to see, and you probably have seen, because we're actually doing this out of order, that I give a lot of names and not a lot of formulas, because I am expecting that you can go from that name to a formula. And it's easy for me to type a name, it's not so easy for me to type a formula. So it is important that you be able to go from a name to a formula. And you should also be able to go from a formula to a name. So we need to make sure that we can do both of those 2 things. So we have a formula, we want a name. We have a name, we want a formula. Okay? we still have two cases. So we can talk about our ionic compounds and our covalent compounds, and the rules are different for those two. If we have an ionic compound and we have some formula that we want to name, okay, whatever it is, we list the metal, then the nonmetal. We change the ending of the nonmetal to be IDE, and that is how we do that. Now, the only time that we include anything else is when we're dealing with stuff that may have more than one charge. So we talked about the fact that metals have a particular charge, nonmetals have a particular charge. Sometimes the things that are in these lanthanide and actinide groups, so the middle parts of these metals, they can have multiple charges. And so the only way I know what those charges are is if they're specified in the names that we get. So we could talk about vanadium, which is V. V can be a +2, or it can be a 4. And so when I write names, that would be a vanadium 2 oxide, which means that I have a V2 plus and O2 minus, and that's a VO. Or I could have a vanadium 4 oxide, which is a V2, no, not 2 plus, 4 plus, 4 plus. That's the charge is what's written in that. Oh, dear Lord, you can't see what I'm doing. So vanadium 4 oxide, that's a V4 plus. So the charge is what's written right here. That number refers to the charge on the metal. Okay, oxygen is still a -2, and that means we're going to have a VO2. Okay, so for the metal to nonmetal, the ratio is fixed by the charges on the species that we have. So if we have something that can have multiple charges, we need to indicate what those charges are. So that's going from an ionic formula or ionic name to a formula. All right, so this is our name to formula. When we have a covalent and we have a name to formula, we'll see things like dinitrogen pentaoxide. And so it's this di and this penta that are important. The di means that we have 2 N's, di means 2, and oxide we have 5 because it's a pentaoxide. So those prefixes tell us how many of each thing we have. And that's necessary because when we do a nonmetal to nonmetal, there's no fixed way that these two things can come together. We can have an N2O5, we can have an NO2, we can have an N2O4. There are many different ways. And so we have to specify how many of them we have. Okay, this is going to be a sharing, so there's no complete transfer of electrons. So that's what we're looking at for that. Now, when we talk about going from a formula to a name, if we have an NO2, we have technically a mononitrogen dioxide. And it's always an "ide" at the end rather than oxygen. Okay, now are we required to write the mono? No, that first one we can leave off the mono. If it's a single one, we can say nitrogen dioxide. Okay, if we have an N2O4, that's a dinitrogen because there's 2 nitrogens, and then oh crap, no, that's not. Oh my god. I keep wanting to say 14, and that's French for 4, and that's not what I'm looking for. Greek. Sorry. Prefix 4. Tetra. That's the word I want. Tetra. Sorry. Tetraoxide. Tetroxide is how we say that. And I really am sorry for that. I'm getting old, so sometimes I forget my words and I put in the wrong one. All right, so that's how we go from formula to name for our covalent compounds. Now, when we go from formula to name for ionics, then that's a slightly different story. If we want to talk about formula to name for ionic compounds, then we're going to be looking at something like here's a good one, Mg3PO4 2. Okay, so this is an ionic compound. We have Mg, which is magnesium. And I know that magnesium is an alkaline earth metal, so he has a 2+ charge. Okay. I also know, and I know that because there's 2 phosphorus things there. Now, I know that this is a phosphate because I can find that in the tables that we were given for the tests. So that is a phosphate, and that has a 3- charge, and that's why we get the Mg3PO4 but we don't have to specify any of that in the name, okay? Because again, that's fixed by their charges. The only time it gets weird, again, is if I'm looking at something like NbO2. So Nb is niobium. And I can tell from this that because there's 2 oxygens, which is a total of -4, then there must be a +4 charge on the niobium. And then it's an oxide. So I have to specify what the charge is on the niobium because he's a transition metal. So he's in the center. He's actually right there. So that's niobium. So because he's in the middle there and he could have any number of charges, we need to specify what that charge is, okay? So that's how we deal with the names. Now, there is a flow chart. The crux of this flow chart is what kind of bonding is it? Because that determines what you do with it. So if it's an ionic compound, metal to nonmetal, we name the metal, and then the nonmetal, the end is changed to an IDE. The only time we have to specify anything else is if it's a metal that can have multiple charges. If it's a covalent to covalent, i.e. nonmetal to nonmetal bond, then I'm going to have the name of the thing that's written first, and then the name of the thing that's written second. I'm going to change the N to an IDE, and you need to specify with Greek prefixes how many of each I had, because they can come in different ways. All right, so that's how we do the nomenclature. I have a bunch of practice for this. I'm going to put up the answers for that on D2L, and I hope I can do that in the next 24 hours or so to make sure that you guys can get through that. All right, so again, it's just practice for you. There's a whole bunch of practice, and we'll make sure that we've got that taken care of. Now, I'm going to take a break here, and then we're going to come back, and we're going to talk about, and I think the next one is reactions, concentrations, and stoichiometry. So I'm going to stop sharing. I'm going to stop the recording, and I'll talk to you again soon.